In topology, a mathematical space does not automatically possess boundaries. By default, you are working with an arena of infinite complexity, where points and sets can stretch on without end. The central challenge is determining how to perform meaningful, finite operations when the space you are analyzing could theoretically zoom in forever or expand infinitely outward. To manage this, topologists rely on compactness. This property is the primary mathematical mechanism used to force an infinite space to exhibit predictable, finite behavior. Compactness acts as a structural constraint. It functions as a net, catching mathematical processes before they fall into an infinite regress. James R. Munkres' foundational text, Topology, defines these rules. We will focus specifically on the tools laid out in Chapter 3. We will establish the mathematical definition of compactness, observe how it governs boundaries in Hausdorff spaces, and use it to prove a geometric concept known as the tube lemma for product spaces. Without this property, continuous functions and geometric sequences can escape our control. Compactness provides the necessary constraint for rigorous topology. On page 164, Munkres defines an open covering as a collection of open sets whose union equals the entire space. Immediately below, a space X is compact if every open covering contains a finite subcollection that also covers X. Imagine a one-dimensional line segment covered by overlapping translucent circles representing open sets. You could use infinite blocks, but if compact, the rule ensures you can discard the majority and perfectly cover the structure using a finite selection. To see a space fail this condition, example 4 on page 164 examines the interval from 0 to 1, where 1 is included but 0 is excluded. We attempt to cover this interval using open sets, formulated as the interval from 1 over n to 1, where n is any positive integer. We start with the segment 1/2 to 1, then 1/3, then 1/4. The sets stretch progressively left, inching toward 0. Because 0 is excluded, they become infinitely small and dense approaching that gap, always requiring an infinite number to cover the space. Compare that failure directly to the closed interval, where both 0 and 1 are firmly included. With the 0 boundary included, any open covering must provide a set encompassing that endpoint. Once 0 is covered, the infinite sequence terminates, requiring only finitely many sets. A non-compact space allows mathematical sequences to escape to a missing edge. Compactness binds the space, ensuring finite resolution. This binding enables specific separation rules. At the bottom of page 98, we find the definition for a Hausdorff space, an arena governed by stricter separation than a standard topological space. In a Hausdorff space, any two distinct points can be perfectly separated by disjoint open neighborhoods. Theorem 26.3 on page 165 connects compactness to these rules, stating that every compact subspace of a Hausdorff space is closed. To prove this, we identify a compact subspace, Y, and select a single point x0 that sits completely outside of Y. Figure 26.1 shows the Hausdorff rule. We separate x0 from a point inside the set, like Y2, using disjoint neighborhood circles. Repeating this for every point creates an infinite open covering of Y with overlapping V neighborhoods. Because Y is compact, we know that this infinite covering of neighborhoods can be reduced to a finite subcollection that still covers the space. By taking the union of these finitely many V neighborhoods, we create a continuous boundary around Y. Simultaneously, to find the clear space remaining around x0, we take the intersection of its finitely many corresponding U neighborhoods. Since the intersection of finitely many open sets is guaranteed to remain an open set, the space around x0 stays open. Without compactness, intersecting infinite sets could collapse the neighborhood out of existence. Compactness prevents that collapse, permanently isolating the point. We apply this logic to product spaces. Theorem 26.7 on page 167 posits that the product of finitely many compact spaces is itself compact. Proving this requires a specific geometric tool known as the tube lemma. Figure 26.2 establishes coordinates for a 2D space, x cross y, where y is compact. The proof starts with a 1D vertical slice at x0. Next, an irregular open set N is identified, completely enveloping the slice. The tube lemma guarantees that despite the irregularity of N, there exists a uniform rectangular tube nested strictly inside N that contains the slice. Because the slice is compact, we cover it using finite overlapping rectangular elements within N. Intersecting their horizontal x components creates a single neighborhood W on the x-axis. Extending W vertically generates the uniform tube. The finiteness of the subcover prevents the intersection from shrinking towards zero, which would cause the tube to collapse. Compactness ensures that local, finite control along a one-dimensional slice guarantees uniform dimensional thickness across a two-dimensional space. Compactness transforms infinite, divergent topological variables into manageable, finite frameworks. This foundational logic seamlessly extends our control over one-dimensional lines outward into the precise boundaries of two-dimensional topological cylinders. If the tube lemma secures finite products, what geometric mechanics are required to control the product of infinitely many compact spaces? Theorem 26.7 provides the finite result that prompts that infinite question. The answer lies in the Tychonoff theorem, which pushes topology to its limits by reframing how we understand continuous spaces. Whether isolating a single point or organizing an infinitely dimensioned manifold, the demand for finite subcovers remains the true essence of topological control.